so high. So we will come to new style of talks. Okay? Okay. So once again, I'm deeply sorry for these delays, but we were just rearranging. So let me see. Okay, yes, finally we got it. And you see, I will send you this file. Okay. So the topic of today's talk would be more on functional integral in simpler systems. Point number one is quantization. Using functional integral for free particle. Point number two would be oscillator. Point number three would be fermionic system. Okay. And here we will use Berezin integral. Okay. So brief reminder. For the free particle, we use the following functional integral representation. I over h m x dot square over 2 dt. X of 0 was x0, x of t capital was xt, integral was from 0 to t, and this was integral that was depending on x0 and xt. We interpret I as an integral kernel of the operator we computed it. We showed that functoriality holds. That is,
We checked. Say x0 applied to I was equal to 0. And this is called Schrödinger equation. Now we will come to the issue of local observable. In Feynman picture. So we define the correlator in the following way. This should correspond to the following picture, to the interval with some operator exerted at T1. Sorry, functional integral. Let us find it. For different O of x. Case A, O of x is just x. Then we have the following integral. Dx x of T1. And here again, I have this action. I h m square over 2. And here I put the boundary condition. So how can I do it? How can I compute this object? Using the same idea that I decompose x as x classical plus psi, such that
psi at 0 equals to 0, psi at t equals to 0. So when I plug it in here, I will get x classical at t1 integral, I'm sorry, integral dx exponential plus, sorry, I made some misprints. I'll erase them. Now, what's important is that the second term, this one, is clearly 0. So why the second term is 0?
Because it's odd in psi?
Exactly. So it's easy. Odd in psi. So we know the result. The result is x classical of t1, 1 over square root of t exponential x classical of t. Sorry, not x classical, I'm just writing the formula. So we know this formula already. Okay, now, what happens if I consider small interval? So let t tend to 0. In this case, bracket tend to delta function xt minus x0. Of course, there are some factors like masses and h's here that I just omitted, okay? And pi's, I just omitted these terms. So it is a Gaussian delta function. So it means that the integral over dx x of t exponential is of h tends to what? Tends to x, say t, delta x of t minus x0. It's not very surprising. So it means that operator corresponding to x of t is just a multiplication by x. Not very surprising, but still. However, now we will study a different thing. What if we will put here mx dot at point t1, exponential s of x. So x dot, once again, x dot means dx over dt. So I know what to do. I know that I need to take m, so d over dt, x classical, and I need to multiply by this remarkable function. So I know that x classical is t times xt minus x0 divided by t capital. So d x classical over dt is xt minus x naught divided by t capital. You may call it classical velocity. So I'd like to understand what this is. What is this? It's interesting to note that I can do the following computation. Take d over dx t of this exponential. So what would I have? I take a derivative of the exponent. So I'll get im 2h, and then I take derivative of this quadratic function.
You have an extra factor of 1 over the square root of t.
Yes, thank you. And here I have the exponential. And now I can compare. So even factors of 2 come out properly. Let me put h here. And let me put I here. So up to the sign, I am getting exactly the same formula. So this leads to the famous Feynman quantization. Bifunctional integral. Mx dot corresponds to IH d over dxt. And let me recall that the title of my lectures are Quantum Field Theory with and Without Planck Constant. So today we do it with Planck Constant. And then people liked it so much that they say, look, try to generalize to quantum field theory. Feynman's idea that the object that is called xi are points on the space-time is nothing but the functional integral product over I from 1 to n. And here I have local functions. Fi of the field, its derivative, maybe its second derivative. But here immediately I'll get problems. Problems come out. Okay, and S is integral over X, Lagrangian of phi d phi, d to phi, etc. Naively, okay, when we do it naively, this diverges. Okay, I put 3 exclamation signs. Let me try to explain the origin of divergence. let L be quadratic. Something like d phi Laplacian phi. Not exactly, but something like Laplacian phi. Then I have no problems to define integral over d phi at x1 phi xn. And the result is sum over pairs ij gx. Okay, I can write it down even in the formal way. Let me just change it a bit. My model to write the correct formula. So let me consider complex field for simplicity. And let me put here phi 1, x1, etc. Phi n, xn, phi bar 1, sorry, y1. Phi bar yn. So it's a Gaussian integral. And this is a product. It's actually a sum of a product. I have a symmetric group. And this is the sum of the products of the following way. x1, y, sigma 1. So when I write it like this, I don't write. I'm not writing it as a product. Etc. g xn y over sigma n. So this is symmetric group. And this is multiplied by d phi bar exponential I over h So this formula is called weak formula.
Do
Where
you need d phi bar in the Lagrange?
yes, thank you very much. Of course. Where g, x, y are Green's functions. No problem. Problem appears when I would like to take as O of phi, say phi bar. Because then it means that y goes to x. I need to take it at the same point. And g, x diverges. And this is the origin of so-called ultraviolet problems in Feynman QFT. Okay. But we will try to go, and I think we will do it just after the break. We will try to go with Feynman as far as possible. Yes. Now we will have a 10 minutes break. But before break, let me ask for questions.
I just have a question related to the zero mode I mentioned last time.
Ah, okay.
So in the higher dimensions, a free scalar, the
Yeah.
partition function is the inverse of square root of the determinant of box minus m squared.
Okay, yes.
So that
So it's called infrared problem. Zero mode. It is clear that this expression has no solution. You may ask me why. It's because if I integrate over x, left-hand side is 0. Integral over x, right-hand side is 1. So 0 could not be equal to 1. That's why this is too naive. Actually, and here I need to subtract this zero mode. So how should I write it? I should probably write it in the following form. Something like, so it is, so here I need to fix the shape of the zero mode. Let me call it something like this. U of x is the shape of the zero mode. So how did we get this ease? This ease may be understood as follows. Consider a functional integral and add here the mass term. And here you may add e. So I like to add e's here, some number of e's. So other people like call it determinant of metric. And then here IM has no zero mode. So idea is to compute IM, then take mass to zero. Result would diverge. Of course, like 1 over m. But then you consider I renormalized. You take limit as m is going to 0 of what? Of m times im. And this is infrared renormalization. Interestingly, the shape of the massive regulator survives in the answer. You may call it infrared anomaly. Infrared anomaly means that you have this integral. And with this integral, you assume, you think that you may put m to 0. But when m equals to 0, answer is ill-defined. So you have to run this procedure. So this is the answer what to do with zero mode. By the way, if x has a boundary, and we just put pi at the boundary of x equals to 0, sorry, we do not need to do infrared renormalization. Like we did before, when we had x of t, x capital of 0 equal to 0. Okay, so this is an answer. So I am explaining ups and downs of Feynman integral. So here is the first problem. And this first problem is the divergence of naively understood observables. I'm writing down problems of Feynman integral definition. Of quantum field theory. Problem A. Naively defined observables like functions of phi bar diverge under the integral. There is a problem B. If I consider an integral of something like plus I would like to write it as follows, as integral of x1 small. So there is a yes, x1 small over x, xn small over x, and here I have the integral d phi and here I have f phi bar at x1, etc. f phi bar at xn. Now, when x, say, I goes to xj, this diverges due to gxi xj to some power k. So physicists write it like this. X1, sorry, xi, xj, and these are green functions. Say k of them. If k equals to 1, singularity like g xi xj is integrable. If k is greater than or equals to 2, xi xj. Say, for simplicity, if k equals to 2, then singularity g xi xj square is non-integrable. So physicists call it that loop divergence. Example, let dimension of x be equals to 2. Then green function of xy is nothing. I'm sorry, in this case it is integrable. I'm sorry. Let it be equal to 4. Then green function is 1 over x minus y squared. Gxy times gxy is 1 over x minus y to the power 4. And the integral of d4x, x minus y to the power 4, logarithmically diverges. So actually, it's not a mathematical model. It actually happens in physics. In the Higgs boson theory. That is basically described by Lagrangian, that is d phi star d phi plus moduli phi to the power 4. Okay? So what is the way out? Old way, called renormalize. So it is some ugly procedure. That is a additional prescription added to nice definition of functional integral. So functional integral is this. This is nice plus extra prescription. So new way, go to functorial view on quantum field theory, where problem A just does not happen. We will say that something like phi square is not a local observable. We will discuss it later. Now, what about problem B? Problem B. Diverges when xi goes to xg and cannot be integrated. So now I'll tell you an answer, but we will come to this later on. When we deform quantum field theory by integral over x of O. Okay. We should also deform the concept, not the concept, the local observables. So it means that O, I even put 0 here, O0 goes to O0 plus epsilon delta O0. And we will see then the second order deformation would be just a first order deformation. In the deformed theory. So no problems. I would say no conceptual problems. We will see how it works later. Okay, so what have I explained? I explained pros and cons of functional integral. So what I will do now? I'll give you several things several pros for functional integral. Let me consider another example. Where functional integral works. It's called oscillator. So Lagrangian would be mx dot square over 2 minus what people call k x square over 2. So after some rescaling, I will say that Lagrangian is 1/2 x dot square minus omega square x square. Let me do computations. Computation by functional integral of maps from S1 to R and I will say x of 0 equals x of t. And here I write exponential I over h x dot square minus omega square x square. So it is a Gaussian integral. That is expected to correspond to trace e to the it over hh. Interestingly enough, it is possible to compute this integral. Let me write x equals 2xn e to the in t over t. Okay, I can write 2 pi I, but I actually don't like this 2 pi I here. So what would be if I plug it here? Ah, I'm sorry, I made a misprint. I will get action. It would be an integral over dt. And actually, I will have the following. I will not go into details, but I think that the answer would be something like this. Sum over n. Positive. Sorry, it's already the action. I will not do this easy computation in front of you, just not to waste your time. So n square over t square.
What if n square over t square equals omega square?
So omega is a constant. Okay, so maybe we should do it. Okay, so how do I do it? X dot of t is 2 pi I n xn, and then I have this exponent. So let me call this exponent n. X dot of t squared is 2 pi I n 2 pi I minus n prime xn okay plus n prime. And here I have exp n, and here I have exp n prime. So altogether it gives minus 4 pi squared n prime. Exponential n prime integral over dt times xn prime. Now, this exponential is delta function n plus n prime 0. I put it here, so I get 4 pi squared n squared xn, x minus n. Sorry, I have a sum over n here. N prime. Okay, let me fix some notation. So here I have sum over n. So here are just simple computations. Okay, I forgot something.
Can it happen that for some value of n square over t square equals omega square?
So here I computed this term. Omega is a parameter. So I just take x, plug it here, and compute the integral. So what I computed here. So my claim is that action takes the following form. So how did I got it? So I computed the derivative. It is like this. I forgot 1 over t capital here. So n of t comes as a derivative of the exponent. Then I took a square. After I took a square, I have a product of these two exponents. Then what I actually needed to compute is this. And then I have this n prime coming out, xn prime coming out, and here I have a product of two exponents. And I use the fact that the integral of the product of two exponents is such a delta function. So the double sum goes to a single sum. And this is the expression that I finally get. So here I just made this computation in front of you. What is the question?
My question was, if you tune the value of omega, and you can have the problem of zero.
Yes, we will see it in a moment. So at the moment, omega is general. We will see such a problem. Yes. We will have such a problem. You are absolutely right. And it is called the problem of periodic trajectory. But we will see it later. At the moment, we don't see it. Okay, we see it already here in the formula star. For special omega, we have zero mode. Yes, we do. But still, I want to complete the computation. Now I'd like to take Gaussian integral. And the result would be, of course, before I take Gaussian integral, I just want to say the special case, what happens for so I went too fast. Because this was for n non-equal to 0. Case n equals to 0 should be treated separately. In this case, I will get x naught square omega square. So altogether, I have an integral product for n greater than 0, dxn bar. So here I have complex Gaussian integral. And also I have a real integral of what? And here I have t, of course. And here I have exponential of okay, I made a mistake. This integral contains t inside. The product of integrals. So here action is t times this. And what I have here, I have t, and here I have 4 pi squares n square over t square minus omega square. And here I have xn bar. So it is I. So I want to understand this I, okay? I can formally take this Gaussian integral. Formally, the answer is 1, okay, product of what? So it is 1 over omega square root of t. And here I have what? Product for n greater than 0 to infinity of these guys. Square root of t. For pi squares, n squares over t squares minus omega squared. So we already studied this object. Studied it when omega was equal to 0. Now we study general case. Here we have general case. So this is I. So it is a function of something. So what I will do here? I would like to take, I forgot something, sorry. So here is not a square root. Here I have t. So for each mode, I have this t. So I will do the following. I would like to go to new variable. Let me call z dimensionless variable omega times t. Okay? So how do I do it? I would like to take this t out. Okay? And then we would compare it with so now I call it z with the standard formula for sine of z. But I don't want to jam it. To be continued tomorrow. So just one remark. I just want to make one remark. The denominator has zeros at all integer ends. Is like sine of z. And then we will come to this nice formulas, etc. But we will do it tomorrow. Okay? Since my time is running out. So, any questions up to now?
I have a question in the chat.
I'm sorry. You see?
So the integral of
Yes, it is
Okay.
because the operation of g is total derivative. The left-hand side is 0. Yes, exactly. It's not a stupid question. It's a good question. So if we consider this oscillator, so before I complete computation, you may see that here answer diverges when omega goes to 0. So we may play the infrared anomaly here. Okay. And we will play it. Especially because you are asking this question. So dimension 1 is good because you can do many computations here. You see, this is the infrared anomaly. When omega goes to 0, everything diverges. I will write it here. Omega going to 0, it is infrared anomaly in dimension equals to 1.
and this computation is in Euclidean time.
No, this computation is in Lorentzian time. So there is some number of i's hidden here.
Yes. So you have an infinite product of i's.
Yes. So you may
Then-
ask, then I want to say that this infinite product of i's, okay, yes. You may ask, what does it mean? Of course, I don't like infinite product of i's. So all these infinite products that we have here in this simplest model are pathologies of Feynman prescription. If you want to do things honestly, you have such a thing as an infinite product of i's, infinite product of 2 pi's, etc. Just recall that we never computed the integral over psi fields before. We just extracted it due to functoriality and its property. And here we are trying to compute this integral explicitly. And when you try to compute it explicitly, you see that there are problems. It is not an honest mathematics where we have infinite product of i's. So it's a good question. It's a proper question. And that's why I honestly think that functorial definition of quantum field theory is better. But in order to understand it and to make contact with what is written in the literature, we need to put them side by side. Functorial definition of quantum field theory and Feynman definition, and inspect how one goes into another. And if it really goes, because I have a radical point of view that Feynman description that is written in many books is outdated and should be replaced by functorial one. But before I will say it like this, I need to see pros and cons of Feynman prescription or Feynman integral. I just want to underline that people used to say that Feynman gave a definition. I would say of QFT. I would say that Feynman gave a pre-definition. And pre-definition is something that should be upgraded to make it a definition. So something is a definition if mathematicians could work with it. If people would ask, what do you mean having infinite products of I? Okay, it's an honest question. What do we need? What do we mean having this infinite product like I wrote? What is the infinite product of this n squares minus z squared? Such infinite product diverges. So old point of view is that intuition how to treat these infinite products is called physics. Okay? So I don't like it. In time of Isaac Newton, there was such a thing as calculus of infinitesimals. So mathematicians did not understand what infinitesimals were, while Newton did. And there were physicists like Newton and Leibniz who knew how to operate with infinitesimals. And there were mathematicians who failed to understand it. So calculus in the Newton time is like functional integral in our time. So that's what we will do in this course. We will try to give a mathematical meaning to functional integral. And that's why I discuss its pros and cons on simplest example. Okay? Okay, so I don't want to jam things. Okay? That's why I stopped here. And I will continue tomorrow.